We're starting a new unit on quadratic functions. Quadratic functions are any function whose highest power is an x squared. So we must have an x squared in order to get a quadratic function. Quadratic equations are written in a variety of different forms. So in this lesson, we're going to focus particularly on something called vertex form. And the reason this is called vertex form is because when you look at the equation, it's really easy to tell what the vertex of your parabola is. None of those words sound familiar? That's okay, because that's what we're going to learn in this lesson. So starting out, here is the vertex form of our equation. Y equals a x minus h squared plus k. A is not 0, so we can't have a 0 here out in front, but h could be 0, k could be 0, that's no problem as long as they're real numbers. So a is any number except 0, and h and k are real numbers. The graph of a function like this is a parabola, which is a U-shaped curve. It's not straight lines. You're not going to connect the dots with straight lines. We have to have curves. For absolute value, we definitely had two straight lines. We got to practice our U-shape, and you know it's hard to do a U-shape on the computer, so you'll have to have a little grace for me, and I'll have a little grace for you as well. The parent function, before any transformations happen to it, is f of x equals f squared. So just like with our absolute values in our last unit where we started out with a parent function of f of x equals absolute value of x, and then we changed that up, flipped it, moved it, we're going to look at exactly those same ideas with the quadratic equation, quadratic function. So just like for absolute values, our parabolas, our quadratic equations have a vertex, which is the lowest or highest point on the parabola. So looking at this is our most basic, this is the graph of f of x equals x squared. My vertex is all the way down here at the lowest point. There's my vertex. So it's either going to be the maximum or the minimum, depending on if my parabola is opening upward, as in this case, or downward, which we'll see. Just like our absolute value function, we can flip this over. A parabola also has an axis of symmetry, which divides the parabola into mirror images and passes through the vertex. So on this graph, my axis of symmetry that would turn this mirror image on both sides is the y-axis in this case, not always going to be the case. So that would be the vertical line x equals 0. This is my axis of symmetry. And you can see that the points on either side of this line are symmetric. So this point and this point are both 1 unit away from my axis of symmetry. This point is 2 units away. This point is also 2 units away. So they mirror each other. This one's 3 units away. This is 3 units here. They mirror each other across the axis of symmetry. My axis of symmetry will go through my vertex. And here on the side, I have a table of values for this particular parabola. So it tells me I'm going through -3, 9, -2, 4, and you can see there's some nice symmetry here as well. Around 0, 0 is my vertex here. I have 1s, then I have 4s, then I have 9s. There's some nice symmetry going back up. So you can see it in your table of values as well. So now let's look at some properties of quadratic functions in vertex form. So again, my general equation is y equals a x minus h squared plus k, and I'm going to open up Desmos so we can play around with that a little bit. So here I have in Desmos my equation y equals a x minus h squared plus k. And the nice thing about Desmos actually is it lets me play around with these values. So right now h and k are set to 0 and a is set to 1, and this is my parent function. This is my general parabola y equals x squared. So I'm going to leave that there for you so you can see y equals x squared through the whole thing. But let's see what happens when I start playing around with h and k. So h is inside my parentheses, so you might have an idea of what this does from our work with absolute values. So if I make h, move h to the right, make h positive, my h function, so my whole function shifting to the right. If I move the slider towards the left, my whole function shifts towards the left. Same thing when I move my k towards the right, my whole function is going to shift upward. When I move my k, make it negative, my whole function moves downward. So this works the same way as it did with our absolute values. A negative goes with the h, which means it's doing the opposite of what we think. So a negative 3.3 and a negative is actually going to be like x plus 3.3, but it moved us left. Whereas a positive, if I make h positive, it moves to the right, but there's a negative here, so this is actually x minus 5.8 moved us to the right. And same thing, works the same as the absolute value. It's a plus k, so this is like this whole thing plus 3.1 moved me up 3.1, and if I move it the other direction, I move down 3.1. So you can actually tell that my vertex starts out at 0, 0. That's where my parent function has its vertex. If I figure out what the vertex is of my translated function, you'll notice that those values are the same as h and k. And the reason for this is I take my 0, 0 and I move it 5.8 units to the right. Well, that's going to end me up with an x value of 5.8. Move it 6.5 units down, that ends me with a vertex of negative 6.5. So that means my vertex for my general form of my parabola is h comma k. In other words, looking at the equation, I'm going to take whatever this is, change the sign, because the negative means negative moves me right, positive moves me left, so this is going to be h, even though this is minus h, and k sign does not change. So, for example, if I had the parabola y equals 2x plus 3 squared plus 5, this parabola would have a vertex of, flip the sign of this, so x minus minus 3 means h is actually negative 3, plus 5, so that means k is 5. Don't flip the sign on k. So there we have, there's my vertex. Can pull it right out of the equation when my equation is given in vertex form. The next thing asks me, what is the axis of symmetry? Well, in order to figure that out, let's head back to Desmos. So we can see again that our parent function has this nice axis of symmetry right through x equals 0. And again, that's the line here, x equals 0. So if I change my vertex, so let's say I change my vertex here to minus 3, minus 3, and make k equal to 5. There, I've moved my parabola over. Now it's got vertex negative 3, 5. I'm going to take my slider for c and see if I can slide the line over until it's again, there it is, again, axis of symmetry for my parabola. If I move my parabola the other direction, somewhere over here, then again, I'm going to have to take my axis of symmetry and slide it all the way to the same spot. So you can tell that every time it lines up perfectly with the axis of symmetry, I end up with my x value being the same as my h value. So in this case, the general equation for my axis of symmetry is going to be x equals h. This is my vertical line, the equation of my vertical line. And looking at my example that I got up here, h was, again, negative 3 from my vertex. So this particular parabola has the axis of symmetry of x equals negative 3. So that's your h and k sliding us up and down and left and right. Now we've got to think about a. And again, this is not going to come as a surprise to you based on our work with absolute value functions. But if I take my a value and I make it negative, it essentially flips over my function. Now, it does more than just that, but the first section in your notes asks what happens if a is greater than 0 or less than 0. So if a is less than 0, in other words, a is negative, then my parabola is going to open downward. But if a is positive, my parabola opens upward. So same as with our absolute value function, we're going to flip the parabola over if a is negative. So this is a is positive, then I'm going to open upward, just like my absolute value. This is a is negative, then that means I'm opening downward. Okay, so that's pretty straightforward. Now, we don't have slope like we did with our absolute value function, but the value of a still determines kind of how narrow or wide my parabola is. So if a is greater than, absolute value of a is greater than 1, and you know from solving absolute value equations, that means that either a is less than -1 or a is greater than 1. Either way, I'm going to get an absolute value. This is greater than. Absolute value greater than 1. Let's see what happens. So again, value of a greater than 1. Let me just move this back to 0. I'll move this one back to 0. So we're back onto 0, 0. When my a value is 1, again I have my perfectly normal parabola, and when my a value gets bigger than 1, what ends up happening is my parabola gets narrower. So anything bigger than 1, I end up with a really skinny parabola. Same thing in the negative direction. If I'm at -1, that's just flip it over. And if I go lower than -1, again my parabola gets narrower and narrower and narrower. So this is a parabola that is narrower than my basic parabola y equals x squared. On the other hand, if absolute value of a is less than 1, so this is a is between -1 and 1, go back to our desmos, that would be anything between -1 and 1, so my parabola gets quite wide. Closer I get to 0, the wider the parabola. Then the closer I get to 1, the closer I get to my regular old normal function. And the same thing in the other direction. Closer I am to 0, the wider my parabola. When I get close to -1, it gets close to just being the flipped parabola. So if I'm between -1 and 1, then I am wider than y equals x squared, wider than my parent function. So that's what my a value does to my parabola. So let's take a look at a few examples. Example number 1, we want to graph y equals x plus 3 squared minus 4. The first thing we're going to pull out, even though it says axis of symmetry here first, is to pull off the vertex. And the vertex, I know just by looking at this thing, again, I'm going to need to change the sign on my x plus 3. It's going to actually end up being a vertex at -3. And the -4 moves me down 4, so this is not going to change. My vertex is going to be -3, -4. So if I put that on my graph, 1, 2, 3, 1, 2, 3, 4, there it is, -3, -4. For my axis of symmetry, I know that's going to end up going right through my vertex, but maybe I'll graph a little bit more to make sure. No, let's do it now. So my axis of symmetry, remember, is always x equals h. It's going to be a vertical line, so in this case it's going to be x equals -3 is going to go through -3 straight through my vertex. There's my axis of symmetry. Make sure you label it x equals -3. There's my axis of symmetry. All right, in order to actually graph this thing, we're going to need a few more points. With our parabola, it was pretty easy with the slope. With with our absolute value, it was pretty easy with the slope. With the parabola, it's a little more challenging, but not too bad. So let's try plugging in a few numbers. If I plug in -2, here's my table of values down here that's going to help me out. To plug in -2 into this equation, so I've got y equals -2 plus 3 squared minus 4. Well, -2 plus 3 is 1, so 1 squared is 1 minus 4 is going to be -3. So I've got here -3. So -2, -3, nice point there. Let's see what happens if I plug in a -1. So I've got y equals -1 plus 3 squared minus 4. This is going to be -1 plus 3 is 2. 2 squared is 4. So this is 4 minus 4. Is just 0, so -1, 0. And actually, I'm going to show you a little trick on Desmos that we can actually generate a table of values that will help us out with graphing. So here I've got my parabola graphed already. Here's the vertex, just in case you want to double check. There it is, -3, 4. And in order to generate my table of values, I'm going to go here to the Edit List button. Click there. And this little Convert to Table is going to give me, boom, all the points that I could possibly want that are on the graph. So I've got here -2, -3, -1, 0. Those are the ones I calculated already. It also gives me 0, 5, and a couple points that go whoo, shooting way off the graph, but that's going to be enough for now. So I'm going to put in 0, 5 into my table and onto my graph. Sorry, forgot to graph -1, 0, there it is, and 0, 1, 2, 3, 4, 5, there it is. And because this is a symmetric function, we know that on the other side of my axis of symmetry, if I have 1 point 1 away, I'm going to have another point 1 away. So I don't have to calculate it, I can just figure out where it goes. 1, 2 points away from here, so 1, 2 is going to end up over here. And this is 1, 2, 3, 1, 2, 3 over here. And we want to connect these with a nice curve. So not straight lines. I'm not great at this on the computer. Hopefully you're a little better at doing beautiful curves. And there we go. There is my graph of y equals x plus 3 squared minus 4. Let's try another one. Again, we've got y equals -2 x minus 4 squared plus 8. So I can find the vertex from h and k. Remember, always change the sign. This is x minus h, so this is just going to be a plus 4. And I'm actually going to change my color. Let's do this one in red, so I can keep track of things. Whoops, too much. So this is going to be 4, comma, moves up 8. I'm going to put it on the same graph here. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. There we go. There's my vertex. And again, I'm going to go to Desmos to help me generate some values. So here's my graph with my vertex at 4, comma 8. And again, to get that table of values to help us graph, I'm going to hit this Edit List, Convert to Table, and it gives me not a whole bunch. So I know I've got this 4, 8, and so I actually want to know, let's see, if I plugged in 3, what would I get? So I can actually start typing in values. It tells me I've got the point 3, 6. There's my point 4, 8. I've got this point 2, 0. That seems like might be enough. Let's try it. So I got 4, 8. This is, again, 3, 6. So let's go put that in my table. 3, 6, 2, 0. Oh, looks like I need more. One more. Let's try 1, -10. Will that fit on my graph? Yeah, I think it will. So I'll go with that. 3, 2, 1. 1, -10. And that lets me plot. So this is the point 1, 2, 3, 4, 5, 6, 2, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I forgot to do the axis of symmetry, so let's go back. So I need x equals h. This is going to be the axis of symmetry is x equals 4. So let's put that on the graph because that will help us to be able to do the other points. Straight through x equals 4. And again, we got 1 right on, we got one away, so we're going to have a 1 away on the other side. 2 and 3. This is quite a narrow one because of the -2, and flipped over, which we kind of expected from the -2 as well. So again, as best you can, smooth curves as opposed to straight lines coming down here. It's not as easy as it looks. More or less, there you have it. Not super neat. That's okay. Alright, so now you've learned the long way to graph parabolas, and we're going to look at a shortcut. What is that shortcut, you ask? It's the 135 graphing shortcut. So let's go back to our original graph for a minute. This has something to do kind of like slope, or kind of like rise over run. We notice that the points are symmetrical around the vertex, so we're going to start by the vertex and say, okay, what's the distance? This is again the y distance. When I change 1 in the x direction, I've got a change here of 1, change here of 1. Again, change my y value of 1. This is a change here of 3. Change here from 1 to 4, also a change of 3. From 4 to 9, that's a change of 5. 4 to 9, change of 5. Every time my x value changes 1, I'm changing in this pattern of 1, 3, 5 in both directions. So it's like over 1, up 1, then over 1, up 3, then over 1, up 5, in both directions around our axis of symmetry. And this is going to work for all parabolas where a equals 1. And we're going to see in a minute what to do if a doesn't equal 1, but that's what we're going to start with. So, always starting at our vertex, we're going to say 1, 3, 5. So this is going to be, again, a is 1 or negative 1, that's fine too. This is going to give us a vertex at negative 6, 2. So let's put that on there, negative 6, 2. It's flipped over, so I'm going to be opening downward. That's important to remember. And then again, I have this rule of 1, 3, 5. So 1 over, 1 down, because it's negative. 1 over, 3 down. 1 over, 5 down. And you can check these points with Desmos on your graph or anywhere. So I've got my axis of symmetry going right through the middle of that. Let's pick a different color for that. Axis of symmetry at x equals negative 6. And then again, on either side, I have now 1 over 1 down, 1 over 3 down, 1 over 5 down, and I need to make a nice smooth curve to connect the dots. Nice and smooth. And there you have it. Now, wasn't that easier than plugging in values and trying to figure out where you're doing from here? So remember this rule, 1, 3, 5. Now, what happens when our a value is not 0? So, for example, if I go back and look, actually, let's look at example number 1, where again, our vertex was at negative 3, 4. So, sorry, negative 3, negative 4. So the distance here was 1. The distance from negative 3 to 0 was 3. From 0 to 5, that's 5, and we can count that up on our graph as well. But our second example doesn't quite follow that nice 1, 3, 5 rule, because we have an a value, if you remember, an a value of negative 2. So let's see what happens in that case. So I got my vertex at 4, 8. So from there, from 8 to 6 is 2. From 6 to 0 is 6. From 0 to negative 10, distance of 10. Look at that, it's almost like 1, 3, 5, except everything is doubled. So this is 1 times 2, this is 3 times 2, and this is 5 times 2, because my a value was 2. So it takes my 1, 3, 5 rule and multiplies by a in order to find what my new pattern is. So this would be 1 over, instead of 1 down, it's going to be 2 down. 1 over, instead of 3 down, times 2 is 6 down. 1 over, instead of 5 down, it's going to be 10 down, and we're practically off the graph. So let's try that with example number 4. So I have my vertex at 2, negative 3. So let's put that on the graph. 1, 2, 1, 2, 3. There's my vertex. And then I have my 1, 3, 5 rule, except they're all going to be multiplied by a half, because my a value is a half. So 1 times a half is a half, or 0.5. Half times 3 is 3 over 2, or 1.5. And a half times 5 is 5 over 2, or 2.5. So instead of going, so I'm going to go, this is positive, so I'm going to go 1 over 0.5 up. 1 over 1.5 up. 1 over 2.5 up. So instead of having 1, 3, and 5 as my upward moving, I have 0.5, 1.5, and 2.5. and again on either side of my axis of symmetry. So I'm going to put my axis of symmetry right here through the middle, just so it's nice and visual. Always nice to have arrows on the end to remind me it keeps going forever and ever and ever. And then again, this is 1 away, 2 away, 3 away, and I could keep going up and up and up and up. So then I need to connect them with this nice smooth curve. This is a little bit of a flatter parabola than my other one. Something like that. All right, one more example we're going to put on this graph, and this is the parabola 3x squared minus 8. So spotting your vertex, it looks like our h is actually missing. Our parentheses collapsed. Where did it go? Well, in this case, actually, h is going to be 0 because x minus 0 is still x. So I have 0, comma, negative 8. I'm going to put that on here. 0, 1, 2, 3, 4, 5, 6, 7. There's my vertex, 0, negative 8. And from there, I'm doing my 1, 3, 5 rule, except everything is going to be multiplied by 3 for this value of 3 in front of my x squared. So 3 times 1 is 3, 3 times 3 is 9, 3 times 5 is 15, and so I'm going to go 1 over, 3 up. 1 over, 9 up. So this is 5, 6, 7, 8, 9. 1 over, 15 up, way off the graph. Just lose it. And then put my axis of symmetry through the middle. And can put my extra points on the other side. So 1 away and 2 away from my axis of symmetry. And now I have the challenge of drawing that nice, smooth, curved, narrow parabola. And there you have it. 135 graphing shortcut. So much easier. Example number 6. Tell whether the quadratic has a minimum or maximum value. Then find that value. So, in this case, we're thinking about whether our parabola is opening upward, like our regular parabola, or opening downward, like our flipped parabola. And we know that what determines that is going to be our a value. So when our parabola opens upward, my vertex ends up being a minimum. It's the lowest value on my parabola. But when it's opening downward, it's a maximum because it's the maximum value, the highest value on my parabola. So when you ever need to find a maximum or minimum value, you're always trying to find the y value of the vertex. So the first thing we need to determine is whether this gives us a minimum or maximum based on my a value. Now remember, this comes from a being positive or greater than 0, and a maximum flips it over when a is negative or a is less than 0. So in the case of this example with the 3 over 2, a is positive, a is greater than 0, I'm going to have a minimum. And that minimum value is going to be the value of the y value, y coordinate of my vertex. So looking at my vertex, it's going to be this plus 6 because my parabola, although it moved 5 to the right, moved 6 up. So my minimum value is going to be 6 because it moved 5 to the right and 6 up. And it's coming like that. That's why we have a minimum. So know the difference between whether you've got a minimum or a maximum, and then just pick off the y value. Okay, word problem. Example number 7. Bean Skywalker started as a pilot and was always kind of cocky. Upon returning from a patrol, he requested a flyby. He gave the tower the equation of y equals 1 over 25, x minus 45.6 all squared plus 8.5 as the vector for his approach. That's the path he's going to follow as he comes toward the tower. How close will Ben Skywalker be to the ground on his flyby? Sketch a rough graph of what his flyby might look like. So what we've got, if you're thinking about the graph, it's moved over 45.6 to the right. So I'm just going to sketch this. I'm going to have my minimum point here. And it's moved up 8.5. So here we have on my axis 8.5. And this 1 over 25 is a value that's getting pretty close to 0, so it's going to be a fairly flat kind of parabola. How close will Bean Skywalker be to the ground on his flyby? Well, the closest he gets to the ground is here at the minimum point, which is 8.5. Let's say, so the closest he will be to the ground is 8.5. Let's call it meters. I don't think they said in the question. It's at 8.5 meters. All right, your turn to try it out. 2 questions for you. Pause your video, then come back and we'll work through them. So again, start out by picking out the vertex at 4, 7, and putting that on your graph. So 4, 1, 2, 3, 4, 5, 6, 7. My axis of symmetry is going to be at x equals 4. That's kind of nice to put on your graph. There it is. X equals h, x equals 4. Then I'm going to use my 1, 3, 5 rule. So 1, 3, 5, but in this case it's multiplied by 2. So 1 times 2 is 2, 2 times 3 is 6, and 2 times 5 is 10. So it's going to be 2, 6, 10, and it's negative, so we're going downward. So 1 over 2 down, 1 over 6 down, 1 over 10 down is going to put me right off the graph. And mirror image on the other side. All that's left for you to do at this point is to draw your nice smooth curve. And there it is. I apologize for the waviness of my curves. I could do better on a whiteboard, I swear. All right, number 2, tell whether the quadratic has a minimum or a maximum value, then find that value. So again, minimum or maximum depends upon a, so this has an a of negative 1/4, so I'm going to be flipped over, which is going to mean I have a maximum part. So maximum of, and again, that depends on my y value, so even though it moved 102 to the right, doesn't matter, it's moved 52 up, and that's going to determine my maximum value of 52. All right, now it's your turn. Go get them.